Okay, now let's take a look at question 4. This question says, for each code block below, fill in the blanks so that the function has the desired runtime. Do not use any commas, and if the answer is impossible, just write impossible in the blank. So taking a look at this first code block, we see that the runtime we want to achieve is linear. And that means if we take a look at what this is doing, it's just a simple for loop from I equals 1 to I is less than n, and we want to increment I in some way. And so how do we increment I so we get a linear runtime? A really easy way to do that is to just increment I by 1 each loop, which would guarantee that as our n grows, the number of times we have to iterate through this loop grows linearly with n, which gives us theta n runtime. Taking a look at the second code block, where our desired runtime is now logarithmic, recall that in order to achieve logarithmic behavior, we want to be able to say, for us to get one more iteration out of this for loop, our input n has to double. And so in order to sort of get that behavior where instead of going through from I equals 1 to I equals n linearly, that means we can't add by 1 each time as we did before. We want this behavior of needing to double n if we want one more loop out of this for loop. And so a really easy way to achieve that is instead we can double our I counter every single time. So I multiply equals 2. Moving on to the third code block, where our desired runtime is now constant. That means no matter what our input n is, we want this for loop to just run not necessarily once, but just a constant amount of time. And in order to guarantee that, no matter how large our n gets, we only go through this for loop a constant amount of time, a really easy way to ensure that is to just increment our counter by n each time. And that means we start at I equals 1, and then we immediately increment our I by n, and we know for sure that then that would break us out of this for loop. And so no matter how large our input gets, we are always getting constant runtime. So now let's take a look at part B. Part B is now asking us to do some analysis of these code blocks. So taking a look at this first method F4, it takes in an input, which is an integer n, and within this it says if n is equal to 0, we just return. Otherwise, we make a recursive call 4 separate times on an input that is 1/2 of n, and then at the end we run another function g of n, and g of n runs in theta n squared time. So the first thing that I like to do whenever I see a problem that's recursive is I like to draw out the tree of what those recursive calls would look like. So in this case, we see that we start with an input of size n, and assuming a very large input, meaning that we're not hitting this base case where n equals 0, this n splits off into 4 different recursive calls with input size n over 2. And similarly, each of these n over 2 inputs would continue to split off into 4 more recursive calls. And so if we want to know the total work that this function does, we want to see in total what do all of these recursive calls do, the amount of work that they do summed up together. So this is where this call to g of n comes into play, because this call means that for each of these individual recursive calls to F4, we do around theta of n squared work. So on this top level where we have our input size as n, that means we're doing n squared work here. When the input size is n over 2, that would be n over 2 squared. And same for all of these. And n over 2 squared is just n squared over 4, which asymptotically is still n squared. And this is the runtime for all of these calls, recursive calls, so times 4. But then again, because we're doing asymptotic analysis, we can sort of drop that constant factor, and we see that asymptotically each level of this recursive call tree contributes n squared work. And so now finally we just have to sort of figure out how many levels, or how essentially what is the height of this tree. So recall that when we're doing asymptotic analysis, we also don't really care about what the base of our logs are. And so in this case, the tree, it is splitting off into 4, but each time it's splitting off by dividing our input by 2. And so again, with our logarithmic behavior, we know that if we wanted to increment or increase this tree's height by 1 layer, we would have to double our original input in. So then we can divide one more time and get one more layer out of this tree. So that's sort of logarithmic behavior, which tells us that the height of this tree is log of n. And so overall, we see that in this tree, there's log n levels. And for each level, asymptotically, we're doing n squared work. So in total, this function f4 does theta of n squared log n work. Okay, so now let's take a look at this function f5, which takes in two inputs, an integer n and an integer m. So the first thing to notice is in this for loop, there is a recursive call that we're making to f5. And this for loop goes from I equals 0 to I less than or equal to n mod 10. So what that means is, since we're doing asymptotics and we're looking for the worst case scenario, since this is O notation, big O notation, then what's the maximum number of times that we can loop through this for loop given a certain number? If we're given a number that ends in the largest last digit possible, 9, that means that we would go from I equals 0 to I less than or equal to 9, meaning we would go through this for loop 10 times. And so considering this worst case scenario where our number is composed all of 9s, meaning every single time the last digit is 9, then every time we go through this for loop, we're making 10 recursive calls. And so let's do the same thing as I did up here, and let's take a look at what that recursive call tree would look like. So again, another thing to notice is this for loop is looping based entirely on n. M doesn't really play into how many recursive calls we make. At the bottom, we just do this constant work of printing out M, but otherwise M has no effect on our runtime. So for my recursive tree analysis, I'm going to focus only on n. So we start with n, and assuming worst case, it's a number that's just full of 9s. It's composed only of 9s, which means the first recursive call, we go into that for loop, and it loops 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each of these 10 recursive calls calls f5 with n divided by 10. 10. And so on. And because in the worst case, this number is composed entirely of 9s, after we've divided by 10, each of these would spawn out another 10 recursive calls. So I won't draw out the full recursive tree just because I'm running out of space, but we can see how even though now we're sort of splitting off into 10s and dividing by 10 each time, it's the same structure as above. And it's actually that same logarithm behavior where if I wanted to get another layer in this tree, I would have to multiply my original input by essentially by 10 and then add 9 at the end to get the same branching factor. So this is still logarithmic behavior, and we can sort of say or conclude that the height of this tree is log n. Asymptotically, we don't really care about what the base of this log is, so for now, let's just remember that it's log n behavior for the height of this tree. So now let's think about, well, okay, how much work are we actually doing overall? Only work that's being done per for loop is printing out m. And so we can essentially count that as a constant work each for loop. And so this first level, it's just a constant +1 amount of work. On the second level, we branched out 10 times. So that's, and yeah, we branched out 10 times, and for each of those recursive calls, it just does that one print. So to sum up the work from this layer, it's plus 10 number of work. And then on the next layer down, for each of these recursive calls, they branched out into another 10 recursive calls to F5. And so on this third level, it would be 10 times 10, because for each of these, it branches out 10 times. So that's plus 100 on the third level. And so we kind of see the same pattern emerges, where the work that's being done is 1 plus 10 plus 100. And we said that the height of this tree is log n, meaning there's log n terms in this summation, and it'll sum up. It'll sum up to n. And even though this is not a basic summation that we've seen, it's really similar to the summation that you should have seen sometime by now, which is the one where we go from powers of 2 from 1 to n. So recall that if we're summing up the powers of 2 from 1 to 2 to the n, that gives us exponential runtime. But when we're summing up the powers of 2 from 1 to n, that gives us linear runtime. So analogously here, we're summing up the powers of 10 from 1 to n. And asymptotically, we don't really care about any constant factors. And so we can conclude that this also gives us a linear runtime. And this is the total sum of all the work that all of these recursive calls will do. So overall, we can conclude that our final answer is O of n linear. So part D is looking at empirical asymptotic analysis. So if we're looking at this in the spring 2018 semester, this analysis has actually been made optional, but I'll still go over this exam problem in case you want to see it. So here we are given a table of the runtimes for this method, assign pup jobs, which takes in two lists, a list of puppies and a list of jobs. So there's two inputs essentially. And here we're not doing our analysis on any sort of code. We're doing our analysis based on these empirical values for runtime that we're given. And so note here that we estimate the runtime in terms of n and m, and we're told that the runtime is of the form tilde a n to the b sub 1, m to the b sub 2. And a is approximately 251.9 over 1000 to the b sub 1 times 100 to the b sub 2. So this is all given to us, and our job is to find what b sub 1 and b sub 2 are. So let's start with b sub 1. Using our formula that we're given, I want to sort of write, it's n, runtime of n and m. Do something like this. So let's take those values. So we see that first, our input n is 500. The bigger one. Our input n is 1000, and our input m is 100. So our input n, m, 1000, 100. And then for the second one, let's use 500 and 100. So input for n is 500. Input for m is 100. And so replacing these runtimes with their empirical values, we know that this equals 251.9, and the bottom we know is equal to 125.1. Okay, so now we have on the right-hand side, we see that this is approximately 2. What is the left-hand side now? The left-hand side, let's now use this formula that's given to us. So we can write a to the n. So n up here is 1000, the b1. M up here is 100, b2, divided by a, and then n down here is 500. And then m here is still 100. So now as desired, these two terms cancel out, the a's cancel out, and we're left with 1000 to the b sub 1 over 500 to the b sub 1. And we can replace that and simplify it as 1000 over 500 b sub 1. And that's just the same as 2 to the b sub 1. So to get 2 to the b sub 1 to be approximately equal to 2 from the right-hand side, then b sub 1 just has to be 1 for this equation to be true. Okay, so now we have b sub 1. To get b sub 2, it's a very similar process, so I'll run through that really quickly. So now notice for b sub 2, previously the term we wanted to cancel out was b sub 2 to get b sub 1. Now it's flipped. We want to cancel out b sub 1 to get b sub 2, which means now instead of looking for things where my m is the same, I want to look for the two things that's going to give me the same n. And so I'm going to keep using this bottom row with n equals 1000 and 100. And now I'm going to look for one where n is the same. So I'm going to use this one where n is 1000 and m is 50. So that gives me 251.9 and 30.5. Okay, and then same thing as before, I can match up the run times with the formulas. So on this top one, n is 1000, m is 100. So once again, we can replace that. A 1000 to the b sub 1, 100 to the b sub 2. And then on the bottom with 30.5, n was 1000 and m was 50. 1000 to the b sub 1 times 50 to the b sub 2. Okay, so now the a cancels again, and now the b1 term cancels. So then we're left with 100 over 50 to the b sub 2 equals 251.9 over 30.5. So the right-hand side is approximately 8. Left-hand side, we can simplify that as 2 to the b sub 2 again. And so now we can sort of clearly see if we raise 2 to the 3, that's going to give us 8. So b sub 2 is equal to 3. And that is all for question 4.